So let's just consider now what happens if I drop a wad of paper in the room here. Okay? It's got a mass, so it's going to experience a force negative mg, whatever its mass is, times force of gravity, right? Assuming upward to be positive, gravity then exerts a force in the negative direction. There's also air drag. The faster it goes, the more air resistance there is, so fairly soon it's going to reach a terminal velocity, where the force due to the air drag is equal and opposite to the force exerted by gravity. One model for that, for an object that doesn't get moving too fast, is that the air drag is just proportional to the velocity. Okay? So we would have this. Now, the signs are such that if the velocity is in the downward direction, the drag force, being a negative multiple of the velocity, is in the upward direction. Okay? So this looks like you got two negatives, and it looks like the drag force is adding to the downward force of gravity, but that's not true because the velocity is going to be negative. Okay? Now, that's one possible case. Now, if I jump out of an airplane, hopefully with a parachute, okay? After I open the parachute, I'm kind of subject to this. But before I open the parachute, I'm moving very quickly. And instead of falling relatively smoothly through the air, as a paper wad might, I'm going to create more turbulence, which means I'm going to dissipate more energy. Now, we've had physics, and we kind of understand energy conservation. Not everybody in the differential equation course will understand it as well as this group does. But for energy purposes, you're swirling a lot more air around compared to your velocity, and you would get okay, and gamma and delta are just drag coefficients that depend on the shape of the object, the size of the object, okay? Mainly the size and shape of the object. And in the real world, things are a little bit more complicated than these simple models, but these models work pretty well. Okay, these are the first order effects that you get if you have what's called laminar flow, where the air just kind of flows around the object smoothly, or turbulent flow, where air, where you get some turbulence. And actually, you can even do it like a V cubed if you got a lot of turbulence. Although, when you get to that point, you're really into the Navier-Stokes equations, and nobody can solve them. So, you're still stuck with doing approximations. Anyhow, that's a situation with things moving through a medium. Okay? And you can also think of, dropping a rock into water. You have a drag force from the water. Depending on the velocity of the rock, it'll be more like this or like this. Okay, so what kind of an equation do we get out of this? Well, the net force, which I'll just abbreviate by F net, is just mass times acceleration, which is mass times v prime, which is mass times, if we assume y is your position, y double prime. So we could use any of these to represent the net force. Now, which one of these would we want to use to represent the net force with these rules?
I would imagine him v squared or v prime.
Yeah, because everything's in terms of v. We don't have to go to y. Now we will. you know, put the mass on a spring and all of a sudden you got Y, okay? And that's actually a fairly common thing that we got to worry about. Okay, so anyhow, okay, so we have MV equals negative mg minus delta V, and it's mv prime, of course, or mv prime equals negative mg minus gamma v squared. What kind of equations do we have here? How do you proceed? Huh?
I mean, we just got some linear equation, or well, actually, there's a.
Yeah, well, this one is actually first order linear. This one isn't. It's got a v squared. So what are you going to do with this one?
I guess we can, I mean, when we go to integrate, we can just do integration by parts.
Yeah, you're not going to need integration by parts. It's separable. The first thing you hope for.
Oh, yeah, see, I didn't even think
In
about
most cases. I mean, you can get ugly results with any kind of an equation or ugly expressions to manipulate. Both of these are separable. This one is also first order linear, okay?
Right.
But this one isn't first order linear, so you know, you're more or less stuck with the separable equation.
Right.
Okay, so fairly straightforward though, okay? Well, let's take the first one. What do you get when you try to solve it?